Alrighty. Um, I'm making a new video for direct comparison and limit comparison because apparently I have been feeding you guys false information over the past 2 years. So, in order for us to get fives, I need to make sure that I'm teaching you guys how to do the direct comparison and limit comparison correctly. Oh my Buddha. So here's what the direct comparison is. And as a disclaimer, I'm not a big fan of it, and you'll see why. I'm not a big fan of the direct comparison test, but it's there. So we have two series. We have Series A and Series B. Series B, the second series, is going to be greater than Series A. And here's what's going to happen. If the larger one converges, so if the larger series converges, then the smaller series will also converge. Now, if the smaller one diverges, then by default, obviously the bigger one is also going to diverge. Now, like I said, the reason why I don't like direct comparison is because you have to know that the comparison works for all the terms in terms of direct comparison. The converse might not necessarily be true, so that's why we might have to use the limit comparison test. And we'll see why that happens in the second video. And then you have your little template that we'll use together. All right, so we're going to start off very easy, very basic. Number one. At this point, we should know that the series 1 over n squared plus 1 converges because of the integral test. This is inverse tangent, and then this would just go to pi over 2, not the sum, but the limit. Of course, on the AP exam, we aren't very fond of using the integral test because it kind of takes a while in terms of just find that the function is continuous positive and decreasing. That takes a lot of time. So of course we kind of want these tests in our toolbox to help us, and the direct comparison test is going to help us because it's faster than the integral test. So here's what we're going to do. What we're going to do here is think about the series that we're going to compare this to. So in this case, 1 over n squared plus 1 kind of looks like 1 over n squared. So we are going to, the first step that we're going to do is say that we're going to compare with the series 1 over n squared. Now, this is where it's going to be important for us to look at the comparison. Whenever we are comparing the two series, we're not comparing the series actually. We're actually comparing the terms. So for my second step, which is what I did not do for the other video, we're going to look at 1 over n squared plus 1, and we're going to look at 1 over n squared, and we're going to see which one's bigger and which one's smaller in terms of the sequence, the terms. So you could see that 1 over n squared plus 1, if I were to think about this, is kind of less than 1 over n squared. And this kind of makes sense because if I were to plug in, let's say, some random number, I might have like, if n is equal to 2, then I'm going to have 1/5 and then 1/4. 1/5 is obviously less than 1/4. Now, because we're comparing this with 1 over n squared here, this is where our next step comes in. We know that the series, so not the sequence, but the series now, the series 1 over n squared, what is that? Well, hopefully we know is a convergent p-series, and you're going to have to tell me why, because 2 is greater than 1. Therefore, our original series, n is equal to 1, of 1 over n squared plus 1, converges by direct comparison test. Now, I would prefer you guys to not abbreviate DCT, but you know, that's my thing right there. Please don't abbreviate. Okay, that was easy peasy lemon squeezy. All right, so if I were to look at number 2 here, we're going to do the same thing where I'm going to look at this and think about, okay, this series kind of looks like 1 over the cube root of n squared, aka 1 over n to the 2/3. Now, once again, I need to think about which one is bigger and which one is smaller in terms of my two sequences. Not series, but the sequence. Now, because this is a -2 and this is just a +0 right here, you might think, okay, let's have 1/5 versus 1/7. Well, what's bigger? The 1/5. So then we have 1 over 2/3, and then the cube root of n squared minus 2. Now, notice how for number 1, my comparison was on the right side because this converged, right? Now, notice how here, for number 2, because we're comparing with 1 over n cubed, this should make sense because 1 over n cubed, not n cubed, 1 over n to the 2/3, 1 over n to the 2/3 is going to be a divergent p-series, so it should be on the left side, because if the smaller series diverges, which was what we're comparing with, then the larger series, which is what this is right here, is also going to diverge. Now remember that for step number 3, that you're going to tell me the series diverges, not the sequence, the series. So then we're going to have 1 over n to the 2/3 diverges by p-series. You're going to tell me why. 2/3 is less than 1. Therefore, my original integral, my original series diverges by direct comparison. Easy peasy. Now, like I said earlier at the very beginning of the video, the converse may not necessarily be true, meaning that if you have a, let's say, convergent series right here on the left, and then your original series on the right, we can't do that. So the convergent series should probably be on the right side whenever we are doing our comparison. Likewise, our divergent series needs to be on the left. So if it's like this right here, where our divergent is on the right side, we don't know anything about the original series just yet. It's inconclusive, so we can't use direct comparison. Now, likewise, number 1 and number 2 were kind of easy for us because we thought about this in terms of, let's say, fractions, right? Something like number 13 here or number 11, where I kind of don't know for a fact in terms of which one's going to be bigger and which one's going to be smaller. That's why we're going to have to use the limit comparison test, which is going to be in the next video. But for now, let's go on and do, let's say, one more. Actually, let's do 2 more in terms of number 3 and number 6. Now, for direct comparison, it's not always going to be p-series, but these examples were kind of easy in terms of p-series. You'll see that number 6 is going to be geometric, but direct comparison probably 99% of the time works with p-series and geometric series. Now, for this series right here, we have cosine squared of n and then n cubed plus 1. Now, you might think, I don't know how to compare this with cosine squared of n. Well, remember that the range of cosine squared of n is basically from -1 to 1. But then because, well, actually, no, never mind. The range for cosine is negative 1 to 1. But because this is a square, the range is actually going to be from 0 to 1. So, theoretically, we could compare this with 1 over n cubed plus 1. So for my first step, I'm going to compare this with the series 1 over n cubed. Not n cubed plus 1, n cubed. Okay, and then for my second step, I'm going to think about, okay, which one's bigger? Now, once again, we're just going to pretend that this is 1. So this is just me saying 1 over 2 versus 1 over 3. And we could see that 1 over 2, aka this right here, is bigger. So it's going to be on the right side. So then we have cosine square of n cubed plus 1. And then 1 over n cubed. And then we are just going to tell me, hey, we know that 1 over n cubed converges by p series because 3 is greater than 1. Therefore, my original series converges by direct comparison. Yay. All right, last one. So we have this series right here, and it kind of looks like, let's see, 3 over 4 to the n. So we are going to compare with 3 over 4 to the n. And then I'm going to think about, okay, which one's bigger and which one's smaller. So if I think about this, it kind of makes sense that because we have this plus 5 right here, that this right here is going to be smaller. So then whenever we are, oops, not the series, we're comparing the sequence. So now we have this. So we can see that's because the convergent is on the right side. We could say that the series converges by geometric test because r is equal to 3/4, which is less than 1. Therefore, my original series converges by direct comparison. All right, in the next video, we'll talk about limit comparison and what that is. I like that more, but of course you could do whatever test works for you in terms of the AP exam, if it's an MCQ problem, or on the test, not the test, but the quiz. On the quiz, though, you probably want to make sure that you're doing the most efficient method because you're on a time crunch.